All right. Good morning, good afternoon. Hello, everyone. Welcome. Thank you so much for joining us today, and welcome to the Go Green Work Package 4 webinar. I have to say it's kind of amazing. Our program is coming to a close very quickly and very shockingly sad and wonderful and all at the same time. It's been an amazing journey. So you here today to share with you the various research and results from the Work Package 4 program. So I am Caitlin Southwick. I am the Work Package 8 leader and very excited to be here today as your moderator and joined by two of our top researchers in the program who are going to be presenting the work that they've been doing. Really excited to have you all with us today. Just a couple of quick notes before we get rolling. As always, if you are not speaking, we do appreciate if you keep yourself on mute. If you are having any technical difficulties, usually the easiest thing to do is log out, log back in, but do let me know in the chat if you're having any issues. Today's presentation format is going to be two presentations, first from Patrizia and then from Roberta. We will have time for Q&A at the end of each presentation, and then hopefully time for a little bit of discussion at the end of the webinar. So if you would like to join us in the discussion or the Q&A, I will invite you to unmute yourself and join the conversation. However, of course, we always can use the chat feature. So if you have any questions throughout the course of the presentation, please feel free to pop those in the chat and I will get to those during the Q&A session. Or of course, during the Q&A session, if you would like to contribute, you can always do that in the chat as well. I do have the recording on, as I mentioned. I will also put the captions on. Please let me know if anybody has any questions or needs in that manner. And then otherwise, I am going to go ahead and turn over to Patrizia to introduce herself and her work. So Patrizia, thank you so much for joining us.
Thank you. I will try to share the screen.
All right, we're getting up and running here. Perfect.
Yeah.
Thank you.
Okay, so we can start. So my name is Patrycja Petras. I'm a PhD at University of Neuchâtel and a research assistant in optical arc in Neuchâtel as well. And that's the place where I work on the GoGreen project. It's a very big project, but I'm working on the Work Package 4, which is devoted to the green strategies in conservation, in metal conservation. For my part, I focus on the microbial-based treatment for archaeological artifacts. So what we focus on the Work Package 4 is the green stabilization technologies. So for us, it's important to focus on the green solution. So we aim to find a better way to treat the archaeological artifacts and avoid the chemical compounds and find the alternative for them. It's a really big project, as I mentioned before, so we collaborate internally where we have a lot of interaction between the universities which are participating and also outside where we ask for the opinion for the experts from our field. So as this project is 4 years, so we focus on 4 main blocks. The first one is the selection of the reference materials and methods for the current practice. So that was a big part of our work where we contacted experts, we generated survey and contacted conservators around the world to find the benchmark methods that we will investigate and also to find the reference materials that will suit our project. I will tell you a little bit more about this in the coming slides. The second part was the investigation and reassessment of the historical recipes. So if there are any historical recipes that might be reused or improved to our standards that we have right now with the green criteria. The big part also of this work is the development of the green materials. In my case, is the stabilization of copper and iron objects using the microbial-based solutions. So I will tell you more also in this presentation. And we are also slowly getting to the final stage of our project, where we will actually review our breakthrough methods, historical recipes, and benchmark methods to assess if we manage to get some progress in the green conservation. So, as I mentioned, we focus on the three main aspects. So we wanted to investigate historical recipes, benchmark methods, and innovative sustainable treatments. But to actually do it, it was important to create a good model that will guide us through this part. So we selected several objects to study. First, we focus on the artificially aged coupons, because these give us information about precise corrosion that we have, because we create them in our labs, so we know exactly the composition of them. Once our treatment work on the artificial age coupons, we move to the naturally aged, which are more complex. And now we are also in the final stage where we apply our treatment on the sacrificial objects and with interaction with the museum in some outdoor experiments. So to investigate if our treatment works, we applied analytical protocol to characterize our system. We investigate our objects both with the chemical composition analytical tools, but also the colorimetry, measurements in depth, and many, many more to assess the full picture of our stabilization. So as the first one, we focus on reassessment of the natural recipes, historical recipes. We focus on actually natural tannins, because in survey we had like two main answers about the archaeological objects. Either there was the desalination or tannic acid. Even though tannic acid is still in use in current days, we can also think it as a historical method because it's known for quite a long time. So there was actually the big gap in the study in tannins, that we didn't know if there's any difference between the hydrolyzable and condensed tannins. So if there is any difference if we use the chestnut tannins or, for example, mimosa tannins. So thanks to our collaborator from University of Uva, we got a collaboration with Silava team, which provided us with four different tannins, one condensed and three hydrolyzable that we investigated in our project. So we got our results. We compared natural tannins and tannic acid. In all cases, we managed to create the iron tannic complex. As you can see on this image, before and after, the surface becoming darker and more iridescence. Unfortunately, that's not what we would like to have on our object, especially iridescence. But also we discovered that there is other problem which is related to the recorrosion. As you can see on the image, after 3 days we had like few tiny spots, but after 13 days there was big patches of recorrosion. We observed that in all kind of tannins, except the nutgal, which have the little bit better performance, However, this we don't have that much time, so soon there will be publication that you can read a little bit more about it. The other part is the development and evaluation of performance of innovative green materials. So let's continue with iron. That was a big part of the project where we investigated Meirosima extremophilic yeast. We focus on this specific strain because it's coming from the geothermal fluid. So it comes from the place which is heavily contaminated with chloride and heavy metals, which makes perfect suit to working with the iron objects which are heavily contaminated with chloride. Our idea was to use this strain as a dead biomass to sorb chloride into the cell wall. But we also discovered that there is another action, which is ion exchange between the cell wall of our yeast and the corrosion surface, which actually led to formation of the magnetite. We investigate this one in our lab, doing the Raman spectroscopy analysis, which confirmed the formation of the magnetites. Together with our colleague from UVA, we did the SEM images, which showed that there is the nanoparticles of the magnetite. And together with the work package 4, which focused on the technology, we applied for the time in the Soleil synchrotron facility, where we investigate our objects more in depth to see how far our magnetite is created, if there is any signs of the recorrosion, or if there is a kaganite beneath the magnetite layer. And so far, I can say that our results are very, very promising, and soon we will have a publication on these results. And the last one, which we work on our development, is the performance of stabilization treatment on copper. So in our institute in Neuchâtel, there were long studies on Beauveria bassiana. So we already know that Beauveria bassiana creates the oxalic acid. Once we have the oxalic acids together with copper, we can create the copper oxalate, which forms stable layer on top of the corrosion. So we can think it of as a passivation layer which protect our object. Nevertheless, there was a gap regarding the application of this microorganism. So within the GoGreen, we work on the improvement of application. We focus on the Funori gel because compared to the other gels, it gives us really good gelification point, which is very low, thinking of the temperature, which is very crucial for the microorganism, which cannot withstand high temperature above, for example, 35 degrees. Moreover, what was interesting, Funori, which is the algae, contains a lot of polysaccharides, which give an extra source of sugar for our microorganism. So it creates even more suitable environment for them to grow and to create oxalates. So within this work, we managed to improve the application and also the time of the application. With the other gels, the normal time was around 7 days. With the Funori, we reduced this time to 3 days. Another interesting part is that because we create a very rigid gel, we can really easy remove it from the surface, and we don't have residues on the object, which is very desirable in the case of objects which are very porous or the surface is very rough. In any other materials, it would be difficult to avoid reduce residue of the gel and microorganisms. Another aspect of this gel, it was that we reduced the amount of water that we use in our treatment, and also the gel together with the microorganism is possible to put it to the normal waste, so we don't create a problem for the environment. So we had the chance to communicate our work in several conferences, both related to the conferences for conservation, like Lima Congress, but also where we communicate our work related to the synchrotron facility and our more detailed and more deeper understanding of what's happening in depth of our material. Also, in the coming ICOMCC Triennial Conference, we'll present work which is focusing of comparing the traditional gel that we have for Bulgaria Bassiana and the one that we improved right now. And we have still two publications to explain the mechanism of our work. So stay tuned, and I think there's still a lot of interesting results that you will see from the GoGreen. Thank you.
Amazing. Thank you so much, Patrizia. It's just really exciting to see results. I mean, this has been a project we've been working on for 4 years, and it's amazing to see how much progress has been made. So I would love to open up the floor now for questions. We have a few minutes. If you would like, you are very welcome to unmute yourself and join the conversation. Or if you prefer, please feel free to type any questions that you have in the chat. So while we're waiting on our audience, I do have a question just to kick us off. And this is something that actually came up in research that I was doing a few years ago at the University of Amsterdam around using microorganisms for cleaning stone. And one of the problems that I came across was that the material was not commercially available. So I was wondering, can you tell us a little bit about the availability of this method? Is this something that you need a microbiologist to cultivate the bacteria? Is it, well, in my case, it was bacteria. This is microorganisms. How available is this in terms of use?
So, for example, with the dead biomass, for now, as it is an environmental strain which was isolated in our university, it's available in our place,
Mhm.
but it might be easily produced and sent to the person that want to apply on the object. There's no problem because the dead biomass doesn't require special condition. You can put it into the jar, you can just store it for a year or two. It will not change its properties.
Oh,
Regarding the gel, we are working on the kind of interesting solution right now, which also will provide better shelf life for this kind of treatment. So hopefully soon we'll have more about this one.
amazing. So if someone wanted to test this out, they could get in contact with you and find out more?
Yes, it would be probably much better to contact with Eddie Joseph,
Oh,
as she's my supervisor and she's more from the administrative start. I'm more research. But for now, we have the collaboration with Hume Museum from Spain, France, and Switzerland. And as I know, we are open for more if someone would like that.
wonderful. Well, please feel free to get in touch with Go Green if you would like to hear more, and we'll put you in touch with Edith. I'll share the link in the chat, of course. Wonderful. Does anyone else have any questions for Patrizia at the moment? I do have some more, but I of course want to open up the floor if there's anyone else. Okay. So Patrizia, I just had one more question for you. In terms of the historical research that you did, because of course that's something that I personally feel, we deserve to look at again, relearn what we used to know kind of thing. How did you decide on how did you decide to work with tannins? I mean, there's so many options and there's so many different, uh, yeah, approaches that you could have taken. So Why tannins?
So we have our green criteria, which are important for us, and many of these historical recipes couldn't actually stand up for this criteria. Also, if there were some, they were fairly simple, and there was not much room for the improvement of them. So the tannins were most promising because we can try different kind of plants. Maybe some are more promising, maybe more effective than others. That's why we went to the direction of the hydrolyzable and condensed tannins because no one did this comparison. So yeah.
It's very interesting. And I find it particularly fascinating that you were mentioning that historical treatments are not necessarily green. I think that we tend to assume that if it was, done 100 years ago, it must be sustainable. But that's a really interesting fact. And I did share in the chat with everyone more information about how we are defining green within the Green Go Green project. So please feel free to check out the definition and the parameters that we use to measure the greenness of an object. So, or a treatment, I should say. Greenness of anything, really. So that's really interesting. Well, thank you so much for that, Patrizia. It's really fun to hear a little bit more about the behind the scenes and how you chose what to investigate. So it's fantastic, amazing. Let's see. I know we'll have a little bit more time at the end, but I do just want to give everyone one more chance if you'd like to have a question for Patrizia. Oh, I see we've got a question in the chat. Can you tell where I can find the whole of research for clearance? Um, I'm not quite sure. Are we talking, I think maybe publications? Is that what we're referring to, Namilia? I'm going to say the best place to find all of the information for the research is on the website. So I'll go ahead and share that again. And then Patrizia, that's also going to be on Zenodo. Is that correct?
That's correct.
Fantastic. All right. Well, I'll go ahead and share the Go Green website, and you guys can all find all of the information for this research and all of the research from the Go Green project on the website. That includes all publications as well as more information about the project as a whole. So thank you so much for that question. Wonderful. All right. Well, I think I would love to hear a little bit more. I know that we are going to be talking about some glass research, so I would love to now turn over to my colleague in Italy, Roberta.
Hello, everyone. Hello, and thank you, Caitlin, for the introduction. So I share my screen now. Okay, so you can see my full screen. Okay, fantastic. So, good afternoon, everyone. I'm Roberta Zanini. I am a conservation scientist and a postdoc of the Center for Cultural Heritage Technology. That is one of the center of the Italian Institute of Technology in placed in Venice. And so, as Patricia already introduced you, we are working in the work package 4 of the Go Green. And so, within this work package, I worked for the development of innovative and new protection treatments for glass, for ancient glass, based on the use of silicon nanoparticles. But let me start to introduce you the glass conservation, because I would like to say that glass conservation is not one of the most widely discussed topic within the conservation field, because as historical glass was considered like a stable material that required little or no intervention. And so as a result, most conservation treatments developed over the century were applied, were adapted for from other fields such as conservation or industrial manufacturing. And so, however, these products often failed to meet some of the fundamental principles of modern conservation, including the long-term stability, the compatibility with the original material, the retractability, and of course, the sustainability of the treatments. And this is because when these material age undergo to yellowing or changes the mechanical properties over long periods. And so, in this, for example, in the case of synthetic resin, they cannot be removed once they degrade. So this background highlights the need for a new conservation strategies, a new conservation products for specifically designed for the glass conservation. And so our approach started with the comprehension of the corrosion mechanism of glass in order to well understand how the material transforms over the time. And because the most dangerous factor that triggers the glass corrosion is water, and very briefly, the glass corrosion process involves that the hydrogen ions of the water can penetrate into the glass matrix, starting an ion exchange process with the modifiers ions that are present in the glass. And this ion exchange continues, and the pH of the environment increases, leading to the dissolution of the silica networks. And so, by investigating archaeological glass, we observed that this corrosion process can often lead to the formation of a silica-rich alteration layer that acts as a partial or total protective barrier, showing slowing down the exchange of water and ions between the environment, and reducing the further degradation process. And so, considering these findings, we developed an archaeo-inspired protective treatment based on silica nanoparticles. And our idea is to mimic the protective role of these silica-rich patina that naturally formed on archaeological glass. But in addition, the nanoparticles, we functionalize the nanoparticles with enamine groups that can interact with the incoming hydrogen ions present in the environment. And so, by reducing the interaction at the glass surface, the amine functionalization may help to mitigate the ion exchange process, thereby enhancing the overall protective effect of the silica coating. In addition, this treatment is fully aligned with the conservation principles because it is chemical compatible with the glass, because it's made of the same materials of the glass itself. It is non-invasive, and it is possible to remove and reapply the nanoparticles for a retreatment. And moreover, we patented a novel and green method to produce the silica nanoparticles, a method that is solvent-free and completely in aqueous environment, and it is very fast, so it decreases also the need of a lot of time and energy for the production of these nanoparticles. More specifically, we synthesized the dendritic mesoporous silica nanoparticles that are a subgroup of mesoporous silica nanoparticles that present a radial channels instead of longitudinal channels of the classical mesoporous nanoparticles. And this particular pore morphology leads to a higher surface area and higher functionalization capacity. And so in this way, we can have a more reactive nanoparticles for our purpose. We investigated the physical and the chemical properties of the dendritic mesoporous silica nanoparticles, and we monitored that upon functionalization, the nanoparticle exhibits a decrease in surface area and in pore volume, information that is consistent with the successful grafting of the amine groups within the mesoporous framework structures. And moreover, both with the thermogravimetric analysis and the zeta potential measurements, we further confirm the incorporation of the amine groups on the nanoparticle surface and within the nanoparticle spores. To evaluate effectiveness of the protective treatment, we started to deposit via spray the functionalized dendritic mesoporous silica nanoparticles on glass surfaces, and we perform an artificial aging experiment based on a cyclical variation of the relative humidity combined with an elevated temperatures into an oven, and after each aging cycle the glass samples were characterized to evaluate the morphological and the chemical changes. And so, after the artificial aging, with scanning electron microscopy, we observed the formation of corrosion products on the untreated glass samples, which were not present on the treated one. And more interestingly, we observed that the morphology of the nanoparticles surface was modified after the aging process. More in detail, the scanning electron microscopy observation revealed the clear presence of surface alteration on the untreated samples. And using the chemical analysis, we observe the presence of a carbonate-rich deposition on the surface, indicating the formation of alteration products that resulting from the interaction between the moisture, so between the water, the hydrogen ions into the environment, present in the environment with the glass components. Instead, for the treated samples, the most evident observation is that the nanoparticles coating underwent to a substantial morphological transformation during the aging. And the original dendritic structure was not, in fact, longer visible after the aging, indicating that the coating actively interact with the environment. In particular, the exposure to high humidity and high temperature may have induced an etching and a dissolution process of the nanoparticles, and the amine group may have interacted with moisture, suggesting that a nanoparticle may act as like a sacrificial layer, limiting the interaction between the environment and the glass surface. To further investigate the effective of these treatments, we perform also the a chemical investigation using a secondary ion mass spectrometry, the profile analysis, in order to investigate the chemical change, the change in the chemical composition within the surface, from the surface to the bulk of the sample. And the results show that no significant compositional changes in the treated glass substrate was appear. In particular, the hydrogen signal remained constant throughout the analyzed depth, indicating the absence of water into the and proton diffusion into the glass bulk. And similarly, also the silicon and the calcium profiles didn't show a depletion or an enrichment phenomenon typically associated to the glass corrosion mechanism. And in fact, the absence of calcium depleted layer and the stable silicon distribution suggested that the silicate network remain chemical unaltered during the aging. So overall, these results support the protective role of the amine functionalized silica nanoparticles, which were able to preserve the chemical integrity of the glass, even under the accelerating aging conditions. And actually, from a conservation perspective, the proposed treatment is particularly attractive because it's based on a silica, so a material that it's intrinsically compatible with the glass substrate. And moreover, like I said, the treatment is removable and reapplicable and minimally invasive. For further perspective, we want to investigate the chemical changes on the surface of silica nanoparticles because as we can see in this slide, from the beginning to the experiment of the aging test to the final to the end of this experiment, the morphological and the surface of these nanoparticles completely changes, and so we would like to use X-ray photoelectron spectroscopy in order to investigate the chemistry of the nanoparticles and better understand the mechanism, the interaction mechanism of this nanoparticle with the environment. And in addition, we want to perform a long-term artificial aging in order to test the durability of the protective treatments and its long-term effectiveness, because this information can be very useful for implement and estimate the retreatment procedures of these materials. So thank you for the attention, and if you have any question, please ask me.
Amazing. Thank you so much, Roberta. It's so exciting to see what you guys have been working on, and lots of really interesting science in there. So I'm excited to delve into that.
Yeah,
But
a
before
little
we,
bit.
yes, yes, but we love it. We love it. We all nerd out on this stuff here. So this is exactly the right place for this. I love it.
Yeah,
Fabulous. So before we dive into the more technical aspects, and once again, would love to open up to our audience, and please feel free to ask any questions in the chat, or I'll invite you in just a second to join us. I did just want to ask you the same question that we asked Patrizia. I know that you guys have patented the silica nanoparticles. What is the availability? When can I get my hands on this?
Okay, so actually, in a few days, I hope, the paper for the with the synthesis with the new synthesis, the patented synthesis, I mean, will be published, and so each of you can replicate the synthesis and so can produce these nanoparticles and as I said, the synthesis process is very fast, is very easy compared to the synthesis protocol that are available now for producing the same time of the same types of nanoparticles. And so actually regarding the availability, I will say that it will be quite easy to have these nanoparticles available also in the commercial in the market like an environment, because this protocol will allow also the scalability of the production of these nanoparticles that can be quite important for the technology transfer, and so to make these treatments and these materials available for the in the market, and so for using it in real context and real environments, real application.
That's so exciting. I have to say that's one of the things that I find really exciting about the Go Green project is the commitment to make these materials available to conservators like me. So
Sure.
it's really exciting. So so there's two elements to the availability. There's the ability to synthesize this yourself,
Yes.
or there is a commercial component coming up in the future, correct?
Yes. Right.
Just for me to better understand, dumb question. If you were wanting to synthesize this yourself, like what would you need to do that?
You need a microwave.
Wait, really?
Yes,
Okay.
because yes, you need a microwave because it's it's a microwave assisted synthesis. Because using this method, we completely eliminate the need of organic solvents for creating this pore morphology, and so you only need the water catalyzed, so an hydroxy and a sodium hydroxide, so very simple to find, and silica precursors and templating agents. That's all. So the synthesis, yes, the synthesis is very fast. So in 10 minutes you have the nanoparticles ready, and that's it. So yeah, the
You make this sound so simple. It's like I could do it in
Yeah,
my kitchen.
absolutely, absolutely. Yeah,
That's really exciting. That's really exciting. We have a question from Maria
yeah,
in Poland. We were talking, she's asking about the application on
yeah.
GSA glass.
You can apply it. We had like a workshop in April here in Venice, and we tried to apply these treatments with the conservators, both using a spray deposition and like a brush. So, in order to see the difference and the distribution, the homogeneous distribution of nanoparticles on the glass substrate, and in order to see like the coverage of the surface with the nanoparticles, we mix the functionalized nanoparticles that I present you in the presentation with the nanoparticles loaded with a perovskite that are salt fluorescence under UV light. And so using the UV light, the conservators can observe and monitor if the treatments was deposited like very homogeneous on the glass surface. And I would like to say that the nanoparticles are not anchored with the glass surface. They are like deposit on it, and so if you want to remove them, you can simply use the like ethanol or Kimtech like tissue, and the nanoparticles are able to be removed very easily, and so you can retreat the surface without problem.
Oh, that's fantastic. I mean, of course, one of the important things is the
Yes. Yeah.
removability and reversibility of treatments.
Yes.
That's really exciting to hear. Thank you for that. Adam had a really good question that I was also curious about. Do you have any images of the visual impact of the application? And
Mhm.
I'm not sure if you covered this, but how does it affect the aesthetics? How does it affect the look of an object? Is it clear,
Absolutely. Yeah.
translucent?
Uh, I have images, but don't not here. Sorry, but we try to deposit the nanoparticles firstly on a microscope slides, and we observed like an opaque surface. But when we try to deposit the nanoparticles during the workshop, the practical workshop in April, we use like a mock-ups very similar to Roman glass samples with different color, and we saw that on a colored glass surface and with a not so very flat surface, the deposition looks like more transparent and without an opaque effect, maybe due to the contrast of the color, etc. And so, yeah, of course. Another thing that we want to implement now is to reduce the size of the nanoparticles, because if you can reduce the size, of course, or the visual effect on the surface could be more less invasive, and yeah.
Yeah, I think that's always a question. You know, we're looking at new techniques and technologies, and we have all of these criteria, and sometimes there's something that's got to give, and it's like what to us is going to be the priority? Is it the visual result?
Yes.
Is it, you know, the greenness, or is it the durability, you know, how long it can last? So there's a lot of questions there, and I think, yeah, it sounds like right now it does have a little bit of an opaque effect on
Yeah,
clear
sure.
new glass,
Yes.
but in some
Yeah.
other kind of glasses, it might not have as much of an effect on the visual component.
Now, also because if you consider that the Ansend glass, the surface of Ansend glass, it's not like very, very transparent because it's like degraded, like they have an altered effect on the surface. The problem to have like a completely transparent coating, it's less important, let me say. So of course you don't have to modify the appearance of the objects, but the fact that you don't have a very clear and a transparent surface can help in this way. Yeah.
Yeah, absolutely. Just following up on that, I was curious because you had mentioned the artificial aging and you had also mentioned some mock-ups. Have you done testing on actual objects?
Yes.
Okay.
Yes, because we tried on very small pieces of Roman glass samples that we have here in our lab with different color and shapes, and yeah, the appearance is like the same, but of course the treatment is a stabilization treatment, so you can appreciate the effectiveness of the treatments in a long term, and so we want actually to test the how long the nanoparticles like resist to the like a barrier for the interaction with the environment, and so how often you have to retreat the surface with the new nanoparticles, let me say.
Uh-huh. Yeah, that makes sense. That makes
Yeah,
a lot of sense. And I think, there's always that conversation in conservation about, you can test things as much as you want in a lab or with mock-ups or with artificial aging, but until you apply it to a real object, you never know exactly how it's
yeah,
going to react.
yeah,
So
yeah.
very cool. That's very cool. Adam had another question, which is actually a really good point as well. He was
Mm-hmm.
wondering, do you need to cover both sides of the glass? So for example, if you have a bottle or a goblet, or is it just the outside?
I can say that you need to cover the surface in contact with the environment.
Okay.
So if it's a closed object, maybe you need to deposit the nanoparticles only in outside
Okay.
because the object is closed, so there's no great and important interaction with the environment. But if the object is open, maybe it's better to deposit the nanoparticles in each surface in contact with the environment.
Very cool. Very cool. I have a follow-up question on that. Always. Um, so in terms of the idea, of course, is that we have this consolidation effect, and we've got
Yeah.
a protective layer. How does this how is this affected by climate control? So in terms of temperature and relative humidity, does it make it more resistant? Are there concerns there? Do we need to make sure that it's staying in that 40-60 range? Are we happy to have it go outside? What is the impact?
Okay. I don't have the answer,
That's perfect. I love
the
that
real answer
answer.
now because I have to test it. But I would say that considering that the silicon nanoparticles are can be like compare silicon nanoparticles like a very 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 stable glass
Yeah.
because they are made only on silica and without any modifiers that are the main like elements that trigger the glass corrosion. And so I could say, I may say that probably these treatments can be more resistant to the glass itself, and so be more resistant also to the humidity levels, the temperatures, because the humidity during the experiment, the artificial aging that I made, the temperature was 80 degrees and the humidity at 90%, so very, very, very stress conditions. And so I can say that in the common, in the yeah, more normal conditions, they are very, very stable.
Yeah, that's exciting. I mean,
Yeah,
me, I'm all about let's expand our climate control ranges because it's very unsustainable. So it's exciting to hear treatments that can help to protect our objects in those
yeah,
situations.
yeah.
Um,
There is another question.
oh, yeah, we have another question. And this is a good one as well. If the object has broken or has been restored, then what are the implications of
Uh,
applying this treatment on top of something like B72 or
yeah.
an epoxy resin?
Okay, I would say that yeah, as I said, the silicon nanoparticles are made with the same materials of glass.
Yeah.
So it's quite have glass on glass. So if paralloid can be applied on glass, nanoparticles, silicon nanoparticles can be applied on paralloid.
That makes
That's
sense.
the so
I
yeah,
like
yeah.
it.
There's no any implication to
No,
apply these nanoparticles on treated treated objects.
fantastic. Well, that's really, really important, I think, for us to understand as
Yeah.
well. Lauren had a question. You mentioned that the treatment was easily removed. Would regular handling, for example, with nitrogenol,
Mm-hmm.
remove the particles, or do you have to apply the particles after the glass was displayed and in a permanent location in the gallery?
Yeah, that could be an idea. Yes, of course, because if you touch the glass after deposit the nanoparticles, you can remove the nanoparticles. So if you put the objects to be treated in the right location, you can deposit the nanoparticles there, and then you can leave the objects there and yeah, observe and monitor, maybe using the UV light, the presence of the nanoparticles over the time, because you can monitor the presence of nanoparticle using the UV light, because there is this mix of nanoparticles with perovskite. Yeah.
Okay, interesting. So there, it's not, you can't really touch it after you've applied the
No,
treatment.
better no.
That's very good to know. Okay, perfect.
Yeah.
Fantastic. And we have another question from Erin who wanted to know if you've noticed any interactions between the reacted DMSNs from the first application, not entirely removed, and the unreacted DMSNs from a second application.
Have you noticed? Okay, I'm quite difficult to understand the question. Have you noticed any interaction between reacted? No, I perform only one application.
Okay. Okay.
Yeah, and actually, there's no any problem. So the principle is that if you don't remove all the nanoparticles between one application and another one, that's it's not a problem because the nanoparticles like degrade with time.
Mhm.
And so, if you don't remove them, in any case, they remain on the glass surface until they are completely degraded. So that's not an implication to have some nanoparticles between one application and another one.
Yeah.
That's not a problem. Yeah.
Okay. Okay, so that's very interesting. So in terms of the application process, then it usually is just one application.
Yes.
And how long does that application last for?
I have to check it.
Okay.
Because yeah, because I tested the position with the alteration aging for 1 month, but of course with very stressed conditions. But now we want to increase the time of the artificial aging, and we want to monitor the aging and the treatments on a real condition, so without accelerating the aging, and maybe monitor the longevity of these nanoparticles. Yeah.
Fantastic. Fantastic. Well, I very much look forward to continued yeah, research and information as this continues. That's very exciting.
Thank
If there,
you.
yeah, if there are any other questions, please go ahead and put them in the chat. But I would love to ask Patrizia if she would like to join us back today for our final thoughts. And I would just love to ask both of you if you would be willing to share with us kind of we talked a little bit about next steps, but basically, if there's anything that our audience can look forward to in terms of, I know that there's some publications coming out. I know that there's some commercialized products coming out, but tell us what we should be looking out for. So maybe Patrizia, I can put you on the spot to tell us what we can expect coming soon from our microorganisms.
I think the earliest will be the conference I come to see in Oslo,
Great.
which I think is going to be very interesting because we compare the different kind of treatments. But also we are planning 3 publications, one about the mechanism of the meirosema, one which is related to the gels and the tannins. So by the end of the summer, you should look for the publication, and all of them will be available in the link on our website.
Brilliant. Thank you so much. And just a shout out that if any of you are going to be traveling to Oslo in September, definitely please check out the Go Green presentations from Patrizia, but also come join us at the Go Green technical visits, where Roberta will be also presenting the app, which we've been developing in Work Package 6, which is very exciting. So, Roberta, maybe you can tell us a little bit about your future plans for the silica nanoparticles. And if you want to do a quick shout out for the DSA, this is a good time.
Yes, absolutely. Yeah, actually, yeah, a part of the experiment that we want to perform again to understand better the longevity and the properties of the treatments, we want to like understand very well the green impact of these treatments, and because we want to implement our DSA app, so the app that we are developing within the other web package of the Go Green project, in order to evaluate the greenest impact of these treatments compared to the existing one for glass conservation. And of course, we are preparing a publication for this with these results that I show you in the presentation today.
Exciting, fabulous. So, a huge thank you to both Patrizia and to Roberta, not only for your time today, but for all of the incredible work that you guys have been doing. It's really so exciting to see all of this come to life because, we've been working on this for quite a while. So, I do just want to remind everyone, I've just popped the Go Green website in the chat. If you would like to get in touch with us, for example, to test out some of the microorganisms, you can find our contact information on the website. You can also find all of our publications on the website, as well as links to the recordings for the series of webinars that we've been hosting. So, speaking of the DSA, the Decision Support Application, Roberta will be joining us again on the 15th of July, so in just a couple of weeks, for our next webinar in the Go Green webinar series, where she will be introducing us to the Decision Support app, telling us a little bit more about when we can expect to get our hands on that. So we're very excited for that. And also, our last work package webinar will be on the 5th of August. We will be joined by Joel Taylor from NICU, who is going to be presenting to us the decision-making model, which is a support tool for decision-making processes at institutions and for sustainable practices. So we have a lot more coming up. The program is wrapping in September, but that just means we're revving up to get you guys some more content. So follow us on social media, check out our website, sign up to our newsletter. Just a huge thank you to all of you for being here with us today, and especially a huge thank you to our presenters for all of the incredible work and for sharing their knowledge and research with us. It's really fun to see, and we look forward to continuing to keep in touch. So thank you so much, everyone. Have a wonderful rest of your day. Thank you, Roberta. Thank you, Patrizia.
Thank
Everyone
you.
stay cool.
Thank you, everyone.
Thank you, everyone.
Thank you, Caitlin. Bye. Bye
Thank you.
bye.